Hi, everyone. Thank you so much for coming to this session. I think we can begin now. My name is Alina, and here with me is my colleague, Alfonso. And we will talk with you about LLM inference in pure Java and how GraalVM can help it. So let's go. Yep, you can see that.
Right. So I'm Alfonso. I work on the GraalVM team on Project Espresso. It's a mind-bending project. It's Java on Java, metacircular JVMs, and all the stuff. That's my weekday job. But on my weekends, I do other stuff that I'm going to show you today.
Yes, right. And I'm Alina. I work on GraalVM as developer advocate. If you have any questions or comments to us, you can find us on GitHub, on social media, and also the project that we will show here today. You can also find it on GitHub and try it out yourself. Yeah, thank you. So what exactly we'll cover today, and we don't have that much time, so hopefully we'll cover everything, but the goal is to cover how you can implement a fast LLM inference engine in pure Java. You might have seen similar projects done in C or Python, and there is nothing wrong with those languages, but we are at a Java conference, and we are confident that we can do the same and even better in Java. So that is something we will show today. Also, we will show how you can do such thing locally. If you've been at the opening keynote yesterday, you might remember that Stefan asked how many people in the room cannot use cloud-based LLMs because maybe there are some restrictions from their employer or because of privacy considerations. So we will show how you can run such a thing completely locally. Then you might have heard that to run any kind of AI-related workloads, you need GPUs. So we will talk about whether or not that is truly the case. And then we will talk about performance optimizations that come from the Java's vector API, but also from GraalVM, GraalVM JIT, and GraalVM native image. And last but not least, there are many people here who are fans of LangJ4j. We are fans as well. So we will see how you can integrate our engine with LangJ4j and use their APIs and features. So I will let Alfonso tell a story of how this project started and came to be.
Right. So once upon a tweet, Andrew Karpathy, a very well-known figure in the AI community, posted this. This was July last year, July 2023. So he implemented Llama architecture in a pure C file, so no PyTorch, nothing. So it's just a regular C file that will compile in any platform, no crazy dependency, anything. And just as a fun project, weekend project. So I thought that if he can do it in C, can we do it in Java? So 2 weeks later, I ported such a repo to run in Java. At the time, was Llama 2, the 7 billion parameter model. That was just the smallest model that could make sense to run, so you could get some interactions with it. I managed to get the JVM to be very close to the C implementation of Karpathy. And at the time, and I want to really remember this figure, the Llama's 2 7 billion parameter runs on Java at 1.5 tokens per second, right? So this, as it may seem obvious, is not very fast. So I basically just shelved the project because, you know, like at this tokens per second, it's just the interaction is just not very good. Which brings us to today. So this is the current state. After Llama 2, I went to a podcast with Adam, and he said, okay, like, you know, this is cool stuff. You should actually go for it. And then, you know, he ignited the spark to actually come with this Llama 3 project. And actually, the reason why we all are here. So the project here's the repo. You can scan it. Just go. You can scroll it. It's a single file, a single Java file with no dependencies, and it's not native dependencies, no Java dependencies at all, nothing, just pure Java, all the inference is implemented there. Besides the inference, there are other features that you need to run the models. You need the parser, you need to read the model from somewhere, you need some quantizations to be implemented so the model is fast. Anyway, so there's a huge list here. Actually, it's missing native image support there, but anyway, we'll see later. Okay. One more thing, so this whole Llama 3.java is based mostly on Karpathy work and Llama CPP. So most of the things that work in Llama CPP, so we support a subset of the models and of the features Llama CPP supports. Right, so we all know about LLMs and the size of LLMs that can be like huge. There's a term for small language models, which I don't like because there's no such thing as small. So you can say like a small LLM, but that doesn't make any sense. So I will prefer to clarify first why I mean with the not so large language model. So this is the big guys, like the very fast cars. It's a model with more than 16 billion parameters. So when I say parameter and weight in this talk, it's referring basically the same thing. But this talk is going to focus on this. So this is the mini of the LLMs. It's economic, it's versatile, you do many things with it. It's not as good, maybe say, as the big car, but it's very capable. But also, and recently we had these even smaller models, like the scooter line, right? So this talk focuses mainly on the minis and the scooters of LLMs. Right.
Yeah, and this is a meme that we added to kind of illustrate that point that LLMs are indeed everywhere right now. So even if you go to Amazon, I saw this meme saying, why would I pay for Claude if I could just go to Amazon and there is this chat assistant that is supposed to help you buy stuff off Amazon. So you can just there for free to go talk to it and say, hey, can you write React app for me? And it will output instead of recommendations the whole code for you. So this is to illustrate that, well, not always you need to pay for LLMs, but also they're indeed everywhere, like on Amazon, but also there are many more places where they are present, right? So those LLMs are now indeed everywhere.
Right, so those are the cloud-based ones, but there are also the smaller models that are also everywhere. So all these vendors, Facebook, Microsoft, Google, Alibaba, they train and ship their models for free with different licenses, but you can just go and download them and run them locally. But even if you don't have to, so if you don't go and download a model, the models will come to you, even if you don't. So Microsoft is shipping RWKV's inference engine to all Windows devices, with the goal, of course, to run small language models, like not so large language models. Apple is also shipping a model on the iPhone. So if you own an iPhone device, maybe now you don't even have to download the model. The phone will come with the model already. As you can see, just 3 billion parameters, just like the minis of the language models. Also, Google is shipping a model in Chrome. So Chrome now, in the dev version Canary, you can talk to a hidden model in the browser, so you can access all your HTML pages and stuff. So, but even if you don't use Windows, if you don't have an iPhone or an iPad, even if you don't use Chrome, JetBrains also shipping a model for you, so to power the line completion feature. This is even smaller model, but you can see. So, and of course, if you have tried the DevOps Genie plugin and use it on any of the local providers, then you are also using a local model, of course. Right, so let's start with the first demo.
So we will show you exactly what's happening under the hood later on, but we decided first let's show what this engine is capable of.
Right. So I can choose ls. This is the llama3.java file. Everything else just like executables, a makefile, a readme.
So the file is what, like 2,000 lines of Java code, right? Nothing else.
Yeah, it's a fairly large file, but I'll talk a little bit about that later. So let's go. So the way I run this is, of course, using JBank, llama3.java. I need to provide a model to it. Let's use the llama 3.2, the 1 billion parameter, and let's do chat. So if I run this, whoops, it will complain about unsafe, but just for the meantime, there's a workaround for native image. That's why we have to use unsafe. In the next release of Graal, hopefully we don't have to use unsafe anymore. The memory segment API is more than enough for this. So let's say hi to the model. Right, so you can see 20 tokens per second. Actually, the first token or two are actually very slow because the JITs.
The JVM, so we are warming up, right?
Exactly. So that's why this model actually faster. So if now should be warm up. So if we say like tell me a joke, now you should get like 46, another one, and so on. Right. So this is a model running locally. It's a stateful chat, so it will remember all the previous conversations. Everything else is cached and so on. So that's the basic interaction you have with llama 3.java using JBank.
Just one more point there. It was, if you notice, the speed at which we were running, right? It was like 46, 48 tokens per second. Remember how we were talking about Llama 2? Granted, this is a smaller model that we are running, but still, the speed is pretty insane. I don't think you can read at that speed. So this is the speed where we are at the moment. Right, and why are we talking about this in the first place? Why would you want to do local LLM inference? So one thing is privacy. As we mentioned before, maybe you don't want to upload, let's say, your project code to ChatGPT or any other cloud-based model, or maybe you have some sensitive data that you don't want to upload anywhere else. So it would be nice to have some kind of local setup where you can run such a thing. Also the cost, so as long as you have the engine and you have the model, you can just run it completely on your machine. You don't need to pay to any external vendor. And then you can have more control over your application, what exactly is happening. You can fine-tune it to your specific needs. So this is why local, but also why in Java, right? So all the previous benefits remain. What is new to Java is there are no native dependencies. We will show you the source code in a bit, but basically it's one source code file for the engine, right? And then you need to provide a model, and this is all you need. You don't need any dependencies whatsoever. And another reason why we want to do it in Java, because we are Java developers, we love Java, and Java gives us many good productivity tools. We can use our favorite libraries, tools, IDEs, and just be very productive staying in our favorite language. Now, let's talk about LLM's engine and what are the bits and pieces that you need to implement, like key components, at least to give you an overview of what you need to do to have such an engine.
Right, so at the very core is the inference part. So actually that's kind of let's say opaque part because it only like spits tokens, but that's not everything. So that's not enough to actually implement the whole pipeline. You need a tokenizer because LLMs do not understand words per se. They understand tokens. Tokens just like a mapping between semi-words and integers. And of course, there's no one best tokenizer. There are like a myriad of them, and you have to implement all the ones that your models use. You have to read the model from somewhere. In this case, we use the GGUF file format from the Llama CPP project.
And so it's also open source, right?
Yes. So actually, it is implemented in C for Llama CPP, so we have to port it, and you do it in Java. And of course, also every model or most vendors have a different way to talk to the model. So the way you prompt the model has different tokens, different combinations, and all this has all custom. So you have to, for every vendor or different model, you have to implement all this stuff. And finally, the sampler. And this is a less obscure, sorry, a little bit more obscure feature, but actually, there's this fine line between creativity and hallucination. And the sampler is what allows you to tweak that line a little bit. So parameters as temperature or top K or top P are the things that can control this fine line. So you also need a sampler for the model.
So a sampler is basically that part that lets you choose how exactly you want to choose the next token, right? It's not always that you want to choose the token that has the highest probability, because you might end up in a situation where you like go in circles, basically. Maybe you want to allow your model a bit more creativity and a bit more like room for improvisation almost. So that's your sampler, right? So how do you want it to be very strict or likely more creative, but also maybe hallucinating a bit more?
Right, so
this slide, Alfonso says that this is a very simple slide and very accessible. Let me know if you agree with Alfonso that that is the case.
Don't be scared, don't be scared. So this is the modern transformer architecture. So this is not even the one on the attention is all you need paper. It's just, this is only the encoder part, but this is like a raw view of the transformer architecture. I won't go into details here, but I will just quickly show how the translation happens. So the idea is to translate this raw, mathy-looking algorithm into Java, right? And I can assure you that it's not that scary, right? So every single operation you see on the left is translated to very reasonable Java code. For example, like here we have some matrix multiplications. This is how you do, it's not even matrix. So like it's just a matrix vector multiplication. So only 2 nested loops. And that's it. Here are the 3 multiplications, and so on. So I wouldn't go into all the lines, but basically you see, oh, the rotary positional encoding thing. Oh, that's the cosines and sine. What is that? So there is some intuition behind the math, but once you get it, just a dozen lines, just 2 loops, and that's it. So the point here that I can guarantee you that every person in this room can understand every single line of Java that's equivalent to the model, and even more. So every single person in this room can get an intuition of how the model behaves. So what gets in, just have a vector, then the vector goes the feedback again into every layer, and at the end you get a vector of probability. So it is not actually that hard, but you have all this mystic around models. So this is so complex, and actually the hard part, because even if you understand how the engine works, the part that is actually magic to me is that you multiply some matrices and this thing starts speaking to you. So that's actually where the magic actually is. And one small detail is that Usually people say that models, LLMs are like next token predictors. That's true, but you don't get like single token. You get a vector of probabilities. So where you have to have a strategy to pick which is the token you want, right?
And that's your sampler, basically.
Exactly,
right?
that's the sampler. So then we use the sampler, and then that's the. It's a little bit, as I mentioned, obscure detail of LLMs, but actually I wanted to point out because the model on itself doesn't give you the next token. It just give you here are the tokens that I think are the most likely, and you have to, as a developer, pick a strategy to actually select them. Right. So one more thing. So weights in the models. You can say, oh, models like complex neural networks, where's my 5-dimensional tensors? No. So in the UAF, so GUF or the regular models you have, all you have is matrices. That's it. So they're all quantized. We'll see a bit later like what quantization is, but just basically a form of compression. And there's this fine detail is that for every single token, you have to read every single weight of the model exactly once. So if you have a 4 billion parameter model, for every single token you do the inference, you have to go to every single weight exactly once, right? So, which brings us to the next question. Is LLM inference actually how expensive it is, right? So if you have for every token, you have to traverse the entire, all the matrices and all the weights, but actually it's not that costly. So Bitcoin is by far much more expensive in compute time compared to inference. Computers are very fast, so you're just really doing like a regular operation. But people complain that, oh no, but I have to download this 4 GB model. But what they know is that for every single token that you do inference on, your computer has to go through 4 GB of memory again and again and again.
So again, like just to stop for a second there. So even this like tiny little nano model that we are looking at, it says here 85K. So that's 85K weights that the model contains, and that's like the tiniest, almost possible one, right? And output to predict every single token, whether that's a word or like one syllable, it needs to go through each of those 85K weights to predict every single token.
Right. So having this previous slide with the one, so every single weight have to be read exactly once. What do you think is the main factor for inference performance? Compute. No, I was bluffing. So memory. Yeah,
close, but
yes. No. Yes.
Brilliant.
So, memory. But memory bandwidth, right? So latency doesn't matter. The amount of memory doesn't matter. Everything that matters is the memory bandwidth. So, and actually, that's the advantage GPUs have today is not the compute, it's actually the memory bandwidth. They have very fast, like video memory that CPUs don't have. I'll talk a little bit later. But basically, if AMD or Intel come with a 4x faster memory next year, we'll have 4x faster inference on CPUs. And finally, the ability to fully utilize that bandwidth is we use Vector API. The OpenJDK teams just keeps pushing these very beautiful APIs that are just a joy to use. We use memory segment and the Vector API to actually push the limits of the hardware and fully be able to utilize the full memory bandwidth of the CPU. Right. So let's take a quick slide about like more or less you get an idea about how the bandwidth differences are. Just you get the regular laptop, this is like a okay standard laptop. Then you get the GPUs. So and the difference again is that GPUs is not the compute that matters, it's actually the memory bandwidth. But also, so because these LLMs, the small ones, you can also actually run them on the server, but not calling to someone else. You can actually run it as part of your application. So and actually servers have a very high, like tons of memory bandwidth, like 16 channels or something like that. And even crazier is that you actually don't need even powerful cores. So a few, like a dozen of ARM cores, low power cores, can actually like satisfy all the memory bandwidth of a server just to run inference locally on the server. Right. So one more thing. So here you see a graph. This chart is actually for GPUs, but for CPUs they're very similar. The gray line just shows the compute evolution over time, and the green one, the memory bandwidth over time. For CPUs, it's very similar. But you can see that CPUs were getting more, or the compute is getting better and better and more, right? And the memory bandwidth is like lagging. So one more interesting detail, and now we'll jump a bit into code, is like for the Llama 3.java, 90% of the inference time is spent doing matrix vector multiplication. This guy here, right? So if you can optimize this operation, you are done. So everything else doesn't matter. It's just 10%. Doesn't matter. Oh, my softmax have to be like parallelized, vectorized. Doesn't matter. The attention needs to be. Doesn't matter. Everything is mostly bottlenecked by the matrix vector multiplication. And of course, we don't use this one. So I'll quickly jump into code. I'll show you how we do matrix vector multiplication. It's going to be quick. So let's go there. Let's go to matmul. So it's a very simple matrix vector multiplication. It's n squared, nothing too crazy. So what we're doing here is just parallelizing the outer loop. So this outer loop is parallelized, distributed among threads, and then we do a dot product in the inside, right? So you see this parallel 4, it's just using in-stream range and then parallel. Nothing crazy, nothing fancy, just regular Java features that anyone could do. And then this dot product. So there's the scalar dot, which is the simple dot product I show you, but also we have a more complex one, which is the vector dot. And yeah, that looks a bit more scary. But actually, it's not that scary at all. So it's using very reasonable vector API operations to speed up. And actually, it's a bit complex here because the matrices are quantized. So it's not like you have a nice array of floats that you can just load the memory and multiply it. You have an array of quantized values. So you need to read the values, unpack them, load them into SIMD registers, and then do all the multiplication. So while this may look actually a bit scary, it is actually not. So it's just a very reasonable vector API implementation for a dot product. So I also wanted to just give you a quick shout out to the code. So this is the header of the code. It's just it's just JBang, of course. I've developed all this Llama 3 using JBang. That's the main tool I use to launch the project and how I develop in general these kind of projects. You can see there's no dependencies, nothing. Just a few options to include the vector module, and that's it. So one more thing. So in this file is like heavily commented. I can scroll a bit, but for example, this is the GUF part, and you see. So the whole code is kind of like very commented out. Say, okay, like now we're going to read this. There's a tokenizer. So all the components you need are in this file, and so the file is 2,200 lines. So people say, oh, but this file is like too big. Well, it contains the inference engine, tokenizers, all the parser for the format, all the quantizations, everything you need to actually, and even more, because we'll show you later. So if you think that this is big, actually, this is smaller than the string class. This is smaller than the hashmap class. This is smaller than the system class. This is smaller than the class. So it's in the same ballpark as array list, really. So array list is a little bit small, like shorter. But come on, so you have all these amazing features in the same size or very similar size to the array list class. Right. So continue. Right. So talking about quantizations.
Yeah. So why we want to bring this up, because we repeated many times by now, memory bandwidth. That is the main predictor of your performance. So how fast the model responds back to you. And if you want to have higher speed, what you can do, right? If memory bandwidth is a limiting factor, you can either get a better, faster memory, or you can go the other way and you can compress the weights so that per the given amount of resources, you can get more throughput because now your weights are smaller. And here you might think that, okay, this might compromise my model. So if I have less information in each of the weights, maybe it will compromise the model. But what we've seen is that larger models are quite resilient to this. You can compress the weights, get higher speed, and still get good, reasonable results. And talking about compressing the weights, we'll talk about quantizations, and we will have this metaphor of a picture as an example.
Right. So who can tell me like what is in this picture? It's like waterfall, what, the mountain? Come on. So if you look at it, it's like, yeah, it's a little bit blurry. It can be like a sky. So you can barely distinguish the shape. Well, because it's a very like heavily like a compressed kind of picture. So let me show you another one. Right. So this uses a bit more colors. Now you can kind of get an idea of what's in the picture. And if I show you the real picture, the full like scale picture, so you can see actually it's a rainbow, right? So, but the point I want to make here is that if you quantize the model, you will get more to the left, right? And in the middle is fine because you as a human and the model is the same thing. So if you quantize it enough, the model will still be able to understand, or in this case, you will be also understand what's in the picture. But if you quantize too much, you start to losing the meaning. And the same thing happens with the model. I think it's a very fine analogy for what quantization is. And it's not exactly compression, because here we're not like reducing the number of pixels of the image or introducing JPEG compression or anything like that. We're just reducing the amount of information every pixel carries. So in the full image, you know, like a full RGB color. Then the less information you have for every pixel, then the harder and harder it becomes to distinguish. Right. So.
Right, so talking about performance, we want to give you an understanding what you should be aiming for, right? So we are talking about tokens per second, but that metric is a bit hard to grasp because how does it translate to what I can perceive as a human as fast or slow, right? And here we have a few charts, and we will talk about human perception. So the first chart here, where we're using 16 bits per weight, that is the default, basically no compression model that you get when you download it from, let's say, Hugging Face. So by default, on a machine such as Alfonso's here, you will get speed of around 3.1 tokens per second. And again, this is not words per second, but tokens per second. So it can be even like one syllable or one character per second. Now, if you quantize by using 8.5 bits per weight, suddenly you get almost 2x speed up, right? Because your weights are smaller, almost twice as small, well, exactly twice as small, but now you have 2x the speed. And then again, if you're using 4.5 bits to quantize your model, suddenly you are almost at 3.5x the speed, and that is in tokens per second. So this is how quantization can help you significantly, like much more improve the speed of your model. But the point we wanted to make here is how does this relate to human perception? So would I feel like the model is lagging behind from what I would expect it to do? So we did a bit of what Alfonso calls napkin math. And those are our calculations of what is like comfortable perception rate for human beings. So anywhere between 5 to 8 tokens per second will be comfortable reading speed for you. So it wouldn't look to you like the model is being delayed and lagging and annoying you by how slow it is. So in terms of performance, the number you need to keep in mind is that this range between 5 to 8 tokens per second is this like minimal acceptable rate for a human being. And then anywhere higher than that will be obviously much better. So this is the number we should be aiming for. Right, should I maybe see if I can switch the cable now?
Right, switch.
I also should have clicked my slides before saying that. Let me. Okay, let's see. Okay, we are here. Right, so why in Java? We talked about this previously before. So we have high performance from Java, and we have even higher performance with GraalVM. Also, now Java offers us those nice, as Alfonso said, beautiful APIs to do such compute-intensive and very close to the native memory kind of workloads. We have great rich ecosystems, so the tools that we can use, but also the applications to which we can bring those LLM inference capabilities. And then we can do more things with the process, again, from our Java application. So let's say maybe we want to cache some things, have even better experience, have even better speed. So this is why we want to show you how to develop such things in Java. And as you mentioned, we both work on GraalVM. So where does GraalVM come into play here? So we keep saying that GraalVM gives you high performance. And what we observed working on this presentation is that GraalVM gives you very good performance for running such engines both on JIT and native image. But first, let's talk about those latest Java APIs and how does GraalVM work with them. So when it comes to the JIT execution mode, where GraalVM acts as your JDK, things just work, TM, but there are very little limitations to when it comes to JIT. When it comes to native image, things are a bit more complicated because for native image, we need to re-implement some things we cannot just run on the JVM like JIT does. So where we are with the native image support of those latest Java APIs. So for the FFM API, we've been introducing support over the last couple of releases. At this point, I would say we are in good stage with native image. You can use this foreign API support flag to enable for native image. And at the moment, up calls, down calls, and foreign memory access work in native image. So you can build applications with native image that are using the FFM API. Now, with Vector API, things are a bit different. We've been introducing support again for the past couple of releases, starting with 21. And now in the upcoming release, GraalVM for JDK 24, we will have even more Vector API operations supported on GraalVM and very fast on GraalVM. And this also works with native image. Why I'm talking about GraalVM for JDK 24? Because in this release, we will be in this presentation, we will be using exactly 24 early access builds. So if you want to replicate what we will be showing here today, you would need to get 24 early access builds, so the very bleeding edge. And the last point here was the latest APIs. We want to thank our colleague from the compiler team. His name is Yurenko. So if you are planning to use Vector API with GraalVM, a big part of that is being done by Yurenko, and a big part of today's presentation is made possible by Yurenko. So go give him a follow on GitHub. He did a great work to support this. Right. And talking about GraalVM, I mentioned performance, right? So we noticed that GraalVM can give us very good performance in our observations. Again, this is not super scientific benchmarks, but something we are confident in based on our observations. GraalVM in the JIT mode, the Oracle GraalVM version, can give us around 15% faster inference. And that is because we have a good Vector API implementation that is still work in progress, but it's already very fast on GraalVM. So comparing to running with C2 JIT, your standard Java JIT, you can get around 15% performance improvement by running on GraalVM. Now, if you want to try the same thing with native image, you need to get, as I mentioned, early access build. You can even get it from SDK Man. It's very convenient. So I will be using 15 early access build, but you just need the latest at the moment, so 15 and higher. Right, and native image. So while we're talking about native image, you know that we have this big goal of having AUT code running as fast on native image as on JIT. And what we observe is that this kind of LLM inference code is very friendly towards native image. It compiles fine on native image, and it's also very fast on native image. And there is one more interesting implementation that we can do on native image that is pretty unique to native image. I don't think you can do anything like that on plain Java or on plain C, where you can pre-parse information as you are building your native executable, and then you can benefit from instant startup times because you did some of that work already at build time, so your time to first token gets really, really low. Now, with that, I will switch to a demo. Does anyone in the room know what is this photo? Why are we showing this building? OK, this is our home in Zurich. So this is Oracle Labs Switzerland office. This is where Alfonso and I work. So we just wanted to show you where this is coming from and where we work on those things. So let's see. I have my Llama 3 project, the same that Alfonso was showing, but I will show a native image version of it. So let's see how that goes. My command will be make native. Very briefly, before I run the compilation, I want to show the exact flags that we will be using. So this is my native image build command. We are unlocking experimental options because those API are still considered experimental in native image. Then the APIs we need will be the Vector API and FFM. Then we are saying I want -03, so I want higher optimization level. And I want MARC native, so please specialize for this particular machine. Then we are enabling preview features because we are using the Vector API. And we have a few additional flags that we will use for optimizations down the line. So let's make native. You can see that we are a bit worried. OK, let's see. Come on.
It worked.
Alfonso was trying to talk me out of doing a demo live and native compilation live. He was like, let's maybe compile ahead of time. But you know, like what is live without a little bit of risk, right? So let's see. So now it will compile. The compilation usually lasts on my machine. It's less beefy than Alfonso's machine. It usually lasts for me maybe like 34 seconds. But I'm not using any tricks. I'm not even using quick build mode. This is fully ready for production with full optimizations in place build. And it lasted 35 seconds. So now that my build is finished, I have my, let me move this higher up. Oh, man. OK, I should have done the long version. Yeah, I have my little llama.3 file that I generated right now. So the fun thing, so the native executable is fully self-contained. It's 23 megabytes, which I would say is pretty small. But one thing that we also could have mentioned before is my jar, if I want to use the jar, is just 73 kilobytes, right? Which is pretty insane. This is your whole LLM inference engine. With that being said and done, let me run my native file. So this is my engine, and I need to pass the model. So I will pick up the Llama 3.2 and 1 billion parameters. And then I need to pass either chat or prompt. So I want to do a prompt, and maybe I want to ask it, tell me a compiler joke. Why did the compiler go to therapy? Because it had a syntax error in its life. Hope that one compiled correctly. OK, we can have different opinions about the sense of humor of our model, but we can see that it works. The speed that I got is 32 tokens per second on my not so beefy machine, so I would say this is good. But one more thing that I want to point out here is I would say this was very fast, right? It's faster than my human perception of speed and text. But Alfonso's opinion is that here you can see we are parsing the file, and then we are loading the model. So overall, it adds up to maybe 1.3 seconds in the beginning for the very first request, which I would say is totally acceptable, but Alfonso decided this is not acceptable. So one more thing that he implemented is that what we can do now is we can pre-parse my model as I'm building the native executable, and this will specialize my native executable for this specific model. By specializing, I mean that it will work with any other models. It will be still fully functional, but it will particularly benefit if I build with metadata of this model, and then I use the exact same model at runtime. This is where I can see this optimization in full speed. So let's see if we can do this. Maybe you can double check that I'm doing this right. So I would need to preload my gguf file, and I need to pass the model that I'm planning to use. So that would be Llama, again, 3.2, 1 billion parameters, and make native, right? Good?
Yes.
OK, let us pray for another second. This is all highly experimental, bleeding edge. That's why you can tell that we are a bit anxious about the build. But, if you risk, sometimes it does pay off. So let's see. In the meantime, yeah, you can use you can see the different information about my build, such as I'm indeed using 24, so the latest and greatest, not even released version of GraalVM that will only go live in spring, but you can already give it a try just as I'm doing here on my machine. Let's see. Now it's creating an image. This time, I must say that it will take a bit longer to build the application because we are doing more work at build time so that it's faster at runtime. You don't have to do this. This is totally up to you. But what we want to show is that you can do this work at build time and then benefit from runtime optimizations even further. So I built the exact same name, so I will just reuse my prompt from before. Only maybe I can ask it something different. So I will once again run my native executable, pass the same model that I have passed during the build time, and I can maybe ask it, what is DevOps? So if you remember, previously we had this around 1 second spent on pre-parsing. Now, as it builds, and maybe I can kill it because I guess we see the point. So what we see here is now we have 0 milliseconds, 0, so truly native startup for this application. And it runs, and it's not some pre-baked prompt. So it does indeed leverage my model and give me live response to my live prompt as I ask it. So I think this is really impressive, and we are very happy. And I think this showcases another great benefit of native image, because here we are combining the best of both worlds. So we are combining the power of Java memory model, because the way this works is we are pre-baking this data into the image heap that is then put into a native executable. So this is only something native image can do, because it will leverage Java's image heap, but then it will be available in the native executable instantly. And this way you can achieve such great instant, truly startup. Now, I see that we are a bit behind on the time, but maybe we can at least do all the demos, right? So yeah. Another thing that we promised to show you is LangChain4j. Maybe as I open this, I can ask how many people in the room are already using LangChain4j? Some, OK. So what we want to show you is the integration of our project with LangChain4j. And this, what I have here, is a complete demo. And this file now with the integration is overall just 100 lines. So very, very slim. And again, this is set up using JBank. And the only dependency that we are bringing in is the actual LangChain4j. And then if you have used it before, you can see that there are some familiar APIs here. So we see our chat message, AI message, response, system message, etc. And here we are implementing the streaming chat model from LangChain4j. Here we are formatting our message to the format in which our model can understand it. Then here we are generating the response, and we are interacting with the user in the way that we are taking an input and then streaming the output back to the user. And to maybe add a bit more variety to our demo, this one we set up in the way we are saying that you are a helpful airline assistant. So let's see how our application will run integrated with LangJ4j. Let me just go to that folder, LangJ4j, and we can run it with JBang. So I need to pass my file, and I need to pass the model that is there. It's the same model that we used before. This one, and I start and I do chat, right? Yep. So it starts, and we can now ask things. So it's set up to be an airline assistant. So maybe you can ask things such as, can I reschedule my flight? Okay, it shows some warnings, but yeah, I'll be happy to help you with your flight. Here are the options. Here are the things that I need to learn from you to reschedule a flight. And again, the speed is around 30 tokens per second, and we can benefit from all the nice features and integrations that LangJ4j gives us. Should we proceed?
Yes.
Yes. Let's go back with the switch. And we talk about performance a lot because we work on GraalVM, so performance is the #1 priority for us. So that's why we will do benchmarks now, I think, right?
Yes. Let's see. Whoops.
Is it working? Yeah, you can click through. All good.
Oops. No.
Optimizations, okay. GraalVM, performance.
Right. Performance. Right. So benchmarks, performance. So this chart,
it's a bit insane. It takes a few seconds to sink in, but like let's walk through.
Right. So in the y-axis, you have tokens per second. So the higher, the better. On the x-axis is model size. So the more you go to the right, the bigger is the model. And you can see the lines just go down. Means that the bigger the model, of course, less tokens per second you get. So the colors. So on blue is Llama CPP, is the de facto inference engine.
Because it's in C native code, so you can hardly be faster than native code.
It's very fast. On the machine that I did the benchmarks, the orange lines are Llama 3.Java. And as you can see, and then there's the dotted versus solid, which is the different quantization. So as you can see, on the top is the solid lines, which is Q4. It's the smallest quantization. So the more you compress your weights, the more tokens per second you get. But the interesting takeaway here is that the larger your model gets, the advantage of native code actually decreases. And actually, there are some reasons for why Llama CPP performs better. Actually, they have very, very optimized handwritten routines to multiply the matrices. And they do some tricks to actually ensure that for smaller matrices, it is actually very fast. But
while our project is written in a nice idiomatic Java that you can read, write, and understand.
Yeah, completely architecture agnostic. All like just the same for all the architectures. So, but this is on this benchmark machine. It's like my 5-year-old like Ryzen machine. But what I want to show you something more interesting is like I have it here, Llama. So everyone knows Llama. Yes. So yeah, great. So Llama is the tool everyone uses to run models locally, right? It's just like a very nice wrapper around Llama CPP. So everything I'll run here is Llama CPP on the background. So powered by Llama CPP. So Llama serve. So this is the default installation I have in my computer. And let's do Llama run. And I will run the latest Llama 3.2, 1 billion parameter as it comes out of the box. Just enter. And there we're there. Right. So in order to make a comparison, apples to apples, I will use exactly the same model as Llama or Llama CPP is using. I will just scroll a little bit here, try to find it. Here it is, right? So this is the model. This is the file where the model is loaded, that Llama is loading, and we're doing the same thing. So we're doing Llama 3, dash model, and chat, right? But there's one more thing. So in order to be a really, really fair comparison, Llama CPP has this, where I cannot find it anymore.
And threads?
And threads. Not this one. The other one. Right. So by default, Llama CPP will use one thread for every performance course I have in my machine. I have 6 performance cores and I think 8 economy cores. So they really try to squeeze the maximum performance. So they are limiting themselves to 6 threads on the performance cores. So in order to make a fair comparisons against Llama, let's use exactly the same. So right. So let's force the process or native version to use one thread. per performance score, something like this, right? And now let's see what we get. So we load a model and say, okay, let's just say, hi, boom. Tell me a joke, something like this. Just this is the Java version running. We get like 35, 31 tokens. Let's see Llama. Hi, 30, hello, something like that. You get 27, tell me a joke. But you get the point. So the interesting number here is the evaluation rate. The prompt we can ignore for now, but it's the evaluation rate. So how much tokens can you do the inference? So what's your inference speed? And we can see here that, as you may have not guessed, and me neither, that actually Java, the native image, is actually outperforming Llama CPP on this machine, on this particular quantization. And it's actually, this is very impressive because it's not only like a Graal. The Graal compiler is, as I call it, like knocking the ball out of the stadium. This is knocking the ball out of the atmosphere, right? So it's insane, right? So you can get even better performance in some configurations using pure Java, right? So yes, one more thing. So we also support other models. I have my personal Hugging Face account. I can quickly show you. I have a bunch, a dozen other models. Oops, a dozen models. I have all the Quen, all the Llama, Mistral, Llama 3, Quen, more Quen, so specializations, Phi also as well. So this is maintained in my personal thing. So it's quantizations that are also compatible with Llama CPP, but that is like a special made for Llama 3.java. Right. So and there we go. Right. So by default we can run Llama 3. But we can also run all these other models. So like Mistral, Phi, Llama, Quen, and I will quickly show you here. So I have all these screen divided by 4, where I will run all of them at the same time. So I'll just like run Mistral here, let's just Llama here, like Phi, my RAM will suffer, but let's see. So like who are you? Just quickly ask you, who are you?
Oops.
Yeah, it's loading, it's loading. Let's just like do the same prompt for the other models, right? Like, there we go. So Mistral is a bit larger model, so like 7 billion parameters. This is Phi. Well, this is sorry. The second one is Llama. So Llama saying all the stuff. So like that's like Phi from Microsoft. Yes, and finally Quen from Alibaba. So right. So you can see all these models run not in exactly Llama. It's a slightly modified version of Llama 3, but it's actually not very hard. All these models are very similar. Only minor changes, very minor changes are needed. I like to say that they're all cousins. So once you have one running, you can run all them all. Right. So this project is basically just a side project I have some help, people like offering some pull requests and stuff. But if you really want to help, please just come in to the GitHub. There's a lot of performance tuning and testing for example, Macs. It doesn't run great on Macs. It can run actually much faster on Macs. Also on ARM servers. And there's a lot of features that actually will be very nice to implement, more quantization, so because we don't support all of them all. And actually, I want to shout out for the TornadoVM guys, because actually, you only have to implement the matrix multiplication, offload that to the GPU. Also for the heterogeneous project in Oracle. So if you can, any of the guys that work on this, if you can offload the matrix multiplication to the GPU, then suddenly the whole inference will run even faster. And of course, we show you a very tiny, very small integration with LangChain4j that also only does the streaming. But if someone wants to have a proper integration with tool calling, all that stuff, it's just very trivial to support. It's just really not big deal. Just parse some JSON and that's it. Perfectly fine. Right. And we can teach these models to give them ears and eyes. So actually, I think vision is actually easier than audio. The only thing I have to implement is the tiny vision encoder, but everything else is the same. So maybe in a couple of weekends, this can be done. So and we can actually feed the models images. The smaller model, actually Llama has the meta release the smaller vision models recently that can actually consume images. So, and with all that, we'd like to
wrap up. Let's wrap up. So our goal today that we hopefully accomplished was to show you how you can implement a fast LLM inference engine in pure Java with no dependencies, and we showed that it's really small as a jar file, but also you can build a very fast, self-contained and native image version of it that can outperform C code in terms of peak throughput. Now, we also think that this project would be very interesting in terms of educational value. It's available on GitHub. Maybe you can use those couple of seconds to scan the QR code and look it up. So it has all the instructions, how you can build it and how you can run it. And yeah, it was a fun thing to work on, and it's definitely very fun to use. I truly think it's a very easy to set up and always have at your disposal local LLM assistant. And with that, we would like to thank you. I hope you like this presentation. We definitely like giving it to you. And please share your feedback with us. I didn't want to say in the beginning, but for Alfonso, this was his first industry conference. So please share your feedback and please be kind to us. And thank you for coming.
All systems are nominal. Initialize Genesis